This section is all about inverses of functions. Let R be a relation. The inverse of R, denoted R to the -1, is the set BA, where AB is an element of R. Okay, let's see what that means. Well, R is your relation, the one that you start with. So it's just a set of ordered pairs. All those ordered pairs are AB. You know, your X and your Y. Well, the inverse, by the way, this does not mean 1 over R. That is not what it means. It means the inverse of R. It just means you flip all your X's and your Y's, and that gives you the inverse. To determine if a graph passes the horizontal line test, let's say we have this graph, looks like that. A horizontal line test means you could draw any horizontal line. If it crosses the graph in more than one point, then it does not pass the horizontal line test. So for this graph, it does not pass the horizontal line test. A function is 1-to-1 if it passes the horizontal line test. That's why that's so important. And 1-to-1 means that it has an inverse. So if you want to find out if a function is 1-to-1, you can perform the horizontal line test, but there are other ways to determine if it's 1-to-1. If it is not 1-to-1, then that particular function is not invertible. Determine the inverse of the following relation, then graph the relation and its inverse, and determine the domain and range of both. Okay, well, I went ahead and put the solution set here so we can see what's going on. You remember this is the greatest integer function, and it looks like this. It's called a step function also. And the domain of this greatest integer function is all real numbers. The range of the greatest integer function would be all of the integers. That's what this little z means. That means the set of all integers. And you can see that's what this is equal to here. It's not equal to any fractions. It's only equal to integers. So if you wanted to find the inverse of this function, you would switch your x and your y around, and you would end up with x equals the greatest integer of y. Which means whenever you graph this one, you would take all of these little steps and you would flip them up. Do you see how that flips up? Every one of these just flipped up. So the blue part of this graph represents the graph of the inverse of the greatest integer function. The domain of this one represents all of the integers this time. Do you see how x is equal to 1, it's equal to 2, it's equal to 3, it's equal to 4. So x in the blue case is all the integers, but what's y? In this case, y is everything. So y is all real numbers, and x is the set of integers. Determine if the following functions have inverse functions. So we just want to know if they have inverses or not. There are a couple of ways you can determine if a function has an inverse. One way is, of course, to determine if it is 1-to-1. If you remember, the graph of the absolute value function looks like this. And if you put a plus 12 on the inside, it just moves to the left 12 places. Well, if you perform the horizontal line test on this one, you can see that it does not pass the horizontal line test, which means this one does not have an inverse function. Okay, that's just one way, probably the easiest way in a case like this. Well, this represents a linear function. Your y-intercept is -5. and your slope is 1 over 1. So it's a linear function that looks something like this. Of course, my graph's not very pretty, but I guess you get the idea. So if you perform the horizontal line test on this one, no matter where you were to draw a horizontal line, it would only touch the graph in one place. That means that this one is invertible. This one does have an inverse. Finding the inverses of functions is pretty simple. First thing that you want to do is switch x and y. Then you want to solve for y, and then write it as the inverse function notation. So let's try that on the first one. Remember, f of x is the same as y. So this is really the same thing as y equals the square root of x plus 5 plus 2. So the first thing we want to do is switch x and y. Now we want to solve this for y. So we're going to subtract 2 from both sides. To get rid of the square root, we're going to square both sides. And then we're going to subtract 5 from both sides. So for a, you have f inverse of x is equal to x squared, x minus 2 all squared minus 5. So this would be the inverse of f. So how about finding the inverse of h? Well, this is the same thing as y equals x minus 3 over 2. First thing that we want to do is solve that, or switch x and y. So we have x equals y minus 3 over 2. Multiply both sides by 2, so we get 2x equals y minus 3. And then we add 3 to both sides. So 2x plus 3 equals y. So h inverse of x is going to be equal to 2x plus 3. Remember that the graphs of a relation and its inverse are mirror images of each other with respect to the line y equals x. This is still true if the relations are functions. We can easily demonstrate this fact by graphing the function f of x equals x minus 1 all cubed plus 2. Look at this red function here. Remember, the x cubed function is that crazy S shape? Well, this minus 1 means we move it to the right 1. The plus 2 means we move it up 2. So this is the function f of x. If you wanted to reflect this over this line, this is the line y equals x right here. If you reflected this graph over that line, it would be this one. So anytime you want to graph the inverse of a function, you reflect it over the line y equals x. Another thing you can think of is you switch all the x's and the y's. Have a look at this point right here. That's the point 1, 2, right? But what is that point in the inverse? It would be the point 2, 1. The point 2, 1 is here. So this point is reflected here. There are lots of different ways that you could go about graphing this function, but that's probably the best way to do it. The key characteristic of the inverse of a function is that it undoes the function. This means that if a function and its inverse are composed together in either order, the resulting function has no effect on any allowable input. What that means is, if you want to compose a function and its inverse, you're going to simply get x. And the opposite is also true. If you compose the inverse with the function, you will still get x. Prove that the two functions are inverses. So what we need to do is show that g of g inverse is equal to x, and that g inverse of g is equal to x. Or you can show just one of them. If just one of them is true, then it should be true. So g inverse goes inside g. So instead of these x's, I'm going to put all of this stuff. So I have negative x minus 3 all over 2x minus 1. And all of that is right there. That's that little x minus 3. That's all over. Now I put 2 times, instead of x, I put all of this. Negative x minus 3 all over 2x minus 1. And there's my plus 1. So what I did was replace this x with all of this. I replaced this x with all of this. Now I need to simplify it. Let's go ahead and get rid of this 2 down here, and I think, yeah, we'll just do that first. So we'll end up with negative 2x minus 6 all over 2x minus 1. Now, if you remember, to simplify a complex fraction, what you want to do is multiply them by the common denominator. In this case, it's going to be 2x minus 1. So, if I multiply this by the first fraction, I get negative x minus 3. Multiply this by the next one, I get minus 3 times all that. Here, multiply by the first fraction, I just get negative 2x minus 6. And then plus 1 times all of that. So now we distribute, clean it up a little bit. Negative x minus 3 minus 6x plus 3 all over negative 2x minus 6 plus 2x minus 1. Let's see. So we have negative 3 plus 3, that's 0. And negative x minus 6x is a negative 7x. All over. Negative 2x plus 2x is 0. And negative 6 minus 1 is negative 7. Well, that reduces to just x. So you have at least proven halfway that g and g inverse are really and truly inverse functions. To fully prove this, you would need to do the same thing for g inverse of g of x. So you would need to take all of g and plug it into these little x's and do the same process for that one.